Hello everyone. Today we're going to work on section 3.5, change of basis. So let V be a vector space, and let's say it has this basis, V1, V2, all the way to Vn. So that tells us that the dimension of V is equal to n, because we have n vectors in the basis. Well, for any vector in V, because this is a basis, it's a spanning set. So we can write every element V as a linear combination of vectors in B. And this A1, A2, all the way to AN, those are scalars. But because this basis is also linearly independent, these scalars are unique. In other words, any vector you choose in your vector space, there's only one way to write it in regards to these vectors. Why is this so? Well, let's suppose that there is more than one way to write a vector. So suppose V belongs to our vector space, and we can write V two ways. Let's say we can write it as alpha 1 V1, alpha 2 V2, and so on, plus alpha n Vn. And also, let's say we can write V as beta 1 V1 plus beta 2 V2 all the way to beta n Vn. Then if we subtract V from itself, we get 0. So let's say, since we're saying V minus V, that's the same thing as alpha 1 V1 plus alpha 2 V2 all the way to alpha n Vn. Subtract beta 1 V1, I'm going to actually put a parentheses around this, plus beta 2 V2 all the way to beta n Vn. This is V and this is V, so if we subtract them, we get 0. Now, if we combine like terms, we see that 0 is equal to alpha 1 minus beta 1 V1, alpha 2 minus beta 2 V2, all the way to alpha n minus beta n Vn. And since V1, V2, all the way to Vn, this is a set of linearly independent vectors because they form a basis, this implies that alpha 1 minus beta 1 is equal to 0, alpha 2 minus beta 2 is equal to 0, all the way to alpha n minus beta n is equal to 0. Because since they're linearly independent, any scalars in front of these VI's have to be equal to 0 if we get the 0 vector. So then we can see that alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, and so on. So in fact, this is unique. V is equal to alpha 1 V1 all the way to alpha n Vn is the same thing as this, because alpha 1 is equal to B1 and so on. I'm going to give you some new notation that we're going to use for the rest of the semester. So let's say B is a vector, so V is a vector space and B is a basis for that vector space. And again, let's say we have a vector V that can be written as a linear combination of vectors in this basis. Here's the new notation. I'm going to make a matrix. It's going to be called the coefficient matrix. And it is going to be an n by 1 matrix. So it's going to be a column matrix. And this number n corresponds to how many vectors you have in the basis. And all I'm going to do, now you have to keep your basis in this order. So this is called an ordered basis. We don't want to move these vectors around in the basis. We're going to keep them just like this. And what I'm going to do is, since v is equal to this linear combination of vectors in the basis, and remember this linear combination is unique, I'm going to write this as alpha 1, alpha 2, all the way to alpha n. And I'm going to keep them in the same order. So this is the first scalar, so it goes in the first entry. The second scalar goes in the second entry, and so on. So this says this is the coefficient matrix of V in terms of this basis B. Now, it's important to keep in mind that V is a vector in your vector space, but this is a matrix in Rn. It's a column matrix. So it's no longer a vector in your vector space, unless your vector space is Rn. Let's look at an example. Here I have the vector space P sub 3. Now remember, P sub 3 is the set of polynomials of degree 2 or less. Remember, this is the dimension of your vector space, this number here. So a basis for V is 1x and x squared. Let's say I have this vector. V is equal to 3x minus 5x squared. I want to know what is the coefficient matrix of V in terms of this basis B. So the very first thing I want to do is I want to write V as a linear combination of these basis vectors in that order. So that's what I'm going to do. V, now this basis is really easy. I need a coefficient in front of 1 plus a coefficient in front of x plus a coefficient in front of x squared. And most of that information is right here. You can see that we have a 3 in front of the x, a negative 5 in front of the x squared, and then we don't have a constant, so let's put a 0 in front of this 1. So now, because we're in the right order, the coefficient matrix is just 0, 3, negative 5. Pretty simple, right? Let's say we have two vectors, v and w, in a vector space V. And the dimension of V is equal to n, and we have some basis, v1 through vn. Well, since we have two different vectors, we can write both of these vectors as linear combinations of these basis vectors. And let's do W in a different color. And let's just look at some properties of the coefficient matrix. So if I want to know what the coefficient matrix of V is in terms of B, well, we have n vectors in the basis, so this is just alpha 1, alpha 2, all the way to alpha n. And the coefficient matrix of W in terms of B is beta 1, beta 2, all the way to beta n. What if we add these? Well, we know if we add V and W, we'll get alpha 1 V1 all the way to alpha n Vn plus beta 1 V1 all the way to beta n Vn. This is going to be equal to alpha 1 plus beta 1 V1 all the way to alpha n plus beta n times Vn. So then the coefficient matrix of V plus W in terms of our basis, well, remember these are in the right order, so this is just alpha 1 plus beta 1, alpha 2 plus beta 2, all the way to alpha n plus beta n. And this is exactly equal to the coefficient matrix of V plus the coefficient matrix of W. If we multiply a vector, so we had the vector v, which was alpha 1, v1, all the way to alpha n, vn, and let's say we multiply it by a scalar. So because I've already used alpha, I want to use a different scalar. So let's say the scalar is sigma. So sigma is just another letter for a scalar. So sigma times v, well, that's going to be sigma times alpha 1 v1 plus sigma times alpha 2 v2. This is just the properties of vector spaces, right? Remember, if we have sigma outside a sum of vectors, because it's a vector space, it distributes to everything inside. And if I want to write this coefficient matrix, well, again, these are in the right order, so I just put the coefficients in the right spaces. And notice that this is equal to sigma times the coefficient matrix of V in terms of this basis. Let's work with an example. Let's say our vector space is R3, and we have two bases for R3. Now this one's obviously a basis. This is the standard basis, and we know and love that one. This one is also a basis, but you might have to convince yourself it's a basis. So let's see. Can we get this vector from these two as a linear combination of these two? No, because we can't get this one from these two. Can I get this one from a combination of these two? The answer is no, because if I subtract a multiple of this one, I'm going to have a 1 here, and I can't get rid of that 1. I can never get a 0 and get a 1 here. And can I get this one from a combination of these two? The answer is no, because I have a problem with this 1. So these vectors are linearly independent. Also, you can check that by just putting them in an augmented matrix, putting this augmented matrix into reduced row echelon form, and you can see if you do that, you're going to get, you can move this one up. You'll have 1, 0, 0, 1, 1, 0, 0, 0, negative 1, 0, 5. And the reduced row echelon form, if you continue this, is going to look like this. So we're going to have one solution because we get the 3 by 3 identity matrix here. So you can see that they're linearly independent. Now this is all a review. And remember that if you have 3 linearly independent vectors, then they span and they form a basis because the dimension of this vector space is 3. So any 3 linearly independent vectors in this vector space also span, which means they form a basis. Okay, so here I have 2 bases, and I'm going to keep them in this specific order. So I don't want to move these vectors around in the basis. Now I'll write these down, and let's say we have this vector in R3. I want to know what is the coefficient matrix of V in terms of B1 and also in terms of B2. The first one's easy. We'll do that one together, and then I'll let you think about the second one. Okay, so remember the basis, B1, is just a standard basis. So this vector V, which is 3, 2, 1, I want to write it as a linear combination of these 3 vectors in B1. Now notice this is B1. Okay, well that's just 3 times this one, 2 times this one, 1 times this one. So the coefficient matrix in terms of B1 is actually 3, 2, 1. It's actually the matrix for V. Okay, now let's try to write the vector V, find its coefficient matrix in terms of the other basis. So I'm going to erase this. but the idea is still the same. I'm going to put my three basis vectors here. 1, 1, negative 1. 0, 0, 1. Sorry, 1, 0, 0. And then the last one is 0, 0, 5. What are the three coefficients that go in front of these three vectors in this specific order? And once I find them, this coefficient matrix is going to be equal to C1, C2, C3. So how can I find them? See if you can find them, and then you write down what you think the coefficient matrix is, and then check it with my answer. So pause the video and do that. Okay, to find C1, C2, and C3, all we have to do is solve the augmented matrix. So put it in reduced row echelon form. 1, 1, negative 1. 1, 0, 0, 0, 0, 5, and then put 3, 2, 1 here. I'm going to, I'm going to add row 2 to row 3. And while I'm at it, let's also subtract row 2 from row 1. Let's do 2 steps at once. And then if we subtract this one, we'll get a 1 here. Now I'm going to switch row 1 and row 2, and I'm going to divide this row by 5. So now I have C1, C2, and C3. Let's double check it. I'm going to erase the C1, C2, and C3, and I'm going to put in these numbers. So 2, 1, and 3/5. Okay, so I get 2 plus 1, that is 3. Then 2 plus 0 plus 0, that's 2. Then negative 2 plus 0, these 5's cancel, plus 3, I get 1. So I found the solution here. And so you can see that this part right here is going to be our coefficient matrix. So V, in terms of our second basis, the coefficient matrix is 2, 1, 3/5. So this was a lot of work. I mean, it wasn't that bad. But what if I asked you, let's say I gave you a bunch of vectors. So let's say I gave you 10 vectors, and I asked you to write these 10 vectors in terms of both of these bases. So for the first one, it's not going to be bad at all. All 10 vectors will be exactly what you see because this is the standard basis. But for this basis, you see I had to do some work here to find the solution. The work will be the same for each vector, because the only difference is you're going to have different numbers here. But it'll take a little bit of time. So what we're going to learn now is something called the change of basis matrix. So that for any vector, if I gave you a bunch of vectors, what you're going to do is you're just going to multiply the vector you see here by this matrix, and you're going to actually find the coefficient matrix of that vector for another basis. So that's the idea. So a change of basis matrix. Let's say V is a vector space with 2 bases, and I'm going to give you them right here, B1 and B2. Now this is for any vector space. It's not just Rn. It's any kind of vector space. So it could be the polynomials. It could also be matrices, 2 by 2 matrices. So any vector space with 2 given bases. And notice that the number of vectors in both of the bases have to be equal. And let's say we have a vector V, and we can write it as a linear combination of vectors in B1. Okay, so this is how we write it. Then we know that the coefficient matrix is C1, C2, all the way to Cn. I want to know what is the coefficient matrix of V in terms of V2. How we're going to figure this out is first we're going to write each basis vector. So you see how we had two bases, and each basis vector right here, because they're vectors in the vector space, and we have this second basis, we can write each one of these basis vectors in terms as linear combinations of the basis vectors here. So that's what I'm going to do. So each VI in our first basis can be written as a linear combination of vectors in V2. And I'm going to show you how I'm going to write these. So V1 is some scalar, let's call it A11 times W1 plus A21 W2 all the way to AN1 WN. So this one here, this one, you see how I have a 1 on the second part? That corresponds to this vector V1. So the next one is going to be A12 W1, A22 W2, all the way to AN2 WN. And the last one is A1N W1, A2N W2, then ANN WN. So the first one corresponds to the W. See how this is the AN1 and this goes with N? And then this one corresponds to the vector. Now how I'm writing these, I'm giving them two numbers, so it should remind you of entries in a matrix. But the entries are kind of like the transpose, because remember you have a matrix A. Usually we write it like this. But notice that I've written the columns, this A11, A21, all the way N1, as a row. So it's actually like working with the transpose. And there's a reason for this, and we'll see it in just a minute. We're not going to skip any steps, but I'm telling you that we're doing this for a reason. So here you can see A11, A12 all the way to A1N, A21, A22 all the way to A2N. Okay, so we can write each one of the basis vectors in terms of the other basis. So our vector V, which we said was, I think we used the letter C. Yeah, C1 through Cn, so we said V was equal to C1 V1 plus C2 V2 all the way to Cn Vn. Well, now I can make substitutions. Instead of V1, V2 all the way to Vn, I can plug in this information here. So this is going to be equal to C1 times, well, let's just copy this, A11 W1 plus A21 W2 all the way to N1 WN plus C2 times A12 W1 plus A22 W2 all the way to AN2 WN, and continue till we get to Cn A1N W1, A2N W2, ANN WN. Just make sure I didn't write anything wrong here. Looks good to me. Now I'm going to regroup this. I'm going to get all the WI's, their coefficients together. So if I regroup it, V is equal to, let's get all the W1s together. So we have C1, A11 plus C2, A12 plus all the way to Cn, A1n, W1. You can see, crossing these out, plus C1, A21 plus C2, A22 all the way to Cn, A2n, W2. Continue this process. And then the last one is going to be Cn, An1 plus C1, An1, C2, An2, all the way to Cn, Ann, Wn. And since we regrouped it, now this is V in terms of our second basis. So notice that V in terms of B2 can be written as C1, A11 plus C2, A12, all the way to Cn, A1n, and then C1, A21, C2, A22, Cn, A2n. Let's continue this. C1, An1, C2, An2, all the way to Cn, Ann. Now it looks like these A's are in the right order, right? Because we have A11, A12, just like a matrix here. This is actually equal to a product. So looking at that, you can notice that we have C1, C2, Cn for each one of these terms here. So this is equal to A11, A12, all the way to A1n, A21, A22, all the way to A2n. Now this is a matrix. This is that matrix A I was talking about in the beginning of this. Times C1, C2 to Cn. So this is a product of this matrix with this one, right? If you multiply row 1 with this column, that will be the first entry. But notice that this matrix right here, in fact, let me do it in a different color here. This matrix was actually the coefficient matrix of V in terms of B1. So I have that the coefficient matrix of V in terms of B2 is the product of a matrix that consists where its columns are the coefficient matrices of our basis vectors times the coefficient matrix of the entire vector V in terms of B1. This matrix right here, we're going to call it the change of basis matrix. I'm going to write this change of basis matrix like this. I'm going to put over here what we're going to call this. This is the change of basis matrix and we're going from B1 to B2. It's going to be a little backwards from what you expect, how I'm going to write this, and there's a reason for it, but I want you to try to memorize this for now, and you'll see later why we're doing this. It'll make more sense. But we're going from B1 to B2. Okay, so the one on the outside, you're going to the one on the inside. So this matrix, I, B2, B1, look at these columns. This column, this column, this column. These columns, if we scroll up, remember how we defined these VIs? You see I have A11, A21, all the way to AN1. If I wanted to write V1 in terms of B2, its coefficient matrix is A11, A21, all the way to AN1, right? And then you can see V2 would be A1, 2, A2, 2, and so on. You can see that this is VI in terms of B2, so V1 actually. And then this one is V2 in terms of B2, and so on. This is Vn in terms of Bn. Sorry, B2. So now let's write this matrix out a little bit better. This matrix I, B2, comma, B1, what this means, and this is how you're going to define it, you're going to take every vector inside B1, which is V1, V2, all the way to Vn. So we're making a partition matrix where we have the columns as the coefficient matrices of taking the basis vectors in B1 and writing them in terms of this basis here. So like I said, it's kind of backwards from what you think. You're going to take the vectors inside this one, the one on the outside, and write them in terms of the one on the inside. And the whole reason for this is because what we want to say is that V in terms of B2 is going to be equal to this matrix, I, B2 comma B1, times V, B1. And so when we multiply these two matrices, this is going to cancel, and we're going to get I times V, so an identity times V, which is just going to get us V, and we're left with this B2 here. All right, let's do a real example of this. So before I give you that example, I also want to tell you that this change of basis matrix that we just saw, this I, B2, comma, B1, it's an invertible matrix. It's a square matrix, and it's invertible. And I want to tell you what its inverse is. It's actually easy to figure out. But notice that if I take I, B2, comma, B1, and I multiply it by a vector, coefficient matrix of some vector, B1, I'll get V, B2. And if I take I, but I switch these two, so this time I'm saying I'm taking the vectors which we were calling W, and if I write them in terms of the vectors in B1, which is terms of V, if I multiply it by the vector V in terms of B2, I'll get V in terms of B1. So to get back to the original, what would I need to do? Well, I would multiply by this matrix here. So I, B2, comma, B1, and then I put, let's move this here, V, B1, and an I, B1, comma, B2, what happens? So this product here gives me VB2. And then if I multiply it with this matrix, I get the original one back. So this is equal to VB1 by this second step here. So this product here is the same thing as just the identity matrix, the n by n identity matrix. Because remember that the identity matrix, if we multiply it with another matrix, we get itself. So here we have two matrices when we multiply them together, we multiply it with this matrix, we get itself. So this is the identity matrix. And so now we have that these two matrices multiplied together give us the identity matrix. So that means that each one is its inverse, right? So this guy's inverse is this one. So from this statement, we get that I, B2, comma, B1, its inverse is equal to I, B1, comma, B2. And this guy's inverse is equal to this one without this negative 1. So maybe I'll write that as well. And we'll do an example of that later. First, let's just do a basic example. Let's say we have V is equal to R2. So the 2 by 1 column matrices. And here I'm going to give you two bases. Both of these bases where we don't work with that much. Neither one of these bases are the standard basis. So 1, 1, negative 1, 1, 3, 2, 4, 3. So one question I could ask you is, are these what I'm calling bases, are they actually bases? So is this a basis for V, and is this a basis for V? There's two vectors. The dimension of this vector space is 2, so all you have to do is show that they're linearly independent. Okay, can you get this vector from this one? No, because if you multiply this one by a negative, you get a positive here and a negative. You can't get both positive. And you can see that you can't get this one from this one. In order to get a 3 here, you have to multiply by 3 over 4. And if you multiply this one by 3 over 4, you get 9 over 4, which is not equal to 2. So these sets of vectors are linearly independent, which means they span because we need 2 of them for a basis, which means that they're a basis. Okay, so the first thing I'm asking is, what's the change of basis matrix going from the basis B1 to the basis B2? And I'm going to write this, what I'm looking for. Let's do it in a different color. I'm looking for the matrix I, which we're calling the change of basis matrix, from B1, don't make that mistake, from B1 to B2. So like I said, it's in the opposite order of what you think it is. We put the starting point on the right and the ending point on the left. So we're going from B1 to B2, B1 to B2. Okay, now that we understand that, let's write what this matrix is. This matrix is equal to, we take vectors from B1, this vector and this vector. Okay, so I'm going to write them here. 1, 1, negative 1, 1. And I'm going to write them in terms of this basis. So B2, B2. Let's do that. So I need to figure out how to write this basis vector 1, 1 in terms of these basis vectors. Let me make this a little bit smaller. Okay. So we're going to put 1, 1 here. I want to find a C1 and a C2 such that we have these vectors 3, 2, and 4, 3. Find the C1 and the C2 that give us this vector 1, 1. All right, so how do I find the C1 and the C2? Well, let's put it in an augmented matrix. This is 3, 2, 4, 3, 1, 1. Put this in reduced row echelon form. Well, I can subtract row 2 from row 1, and I get 1, 1, 0. 2, 3, 1. And then from here, to get rid of this 2, I multiply row 1 by a negative 2, and I add it to row 2. Okay, let's do that. So this becomes negative 2, so I get 0, 1, 1. And then my last step is to subtract row 2 from row 1. And I get 1, 0, negative 1, 0, 1, 1. So I can see that C1 is equal to negative 1 and C2 is equal to 1. Let's just verify that by plugging these in and seeing if we get the right answer. So I'm going to put negative 1 here, and I'm going to put a 1 here. So I get negative 3 plus 4, that's 1. Negative 2 plus 3, that's 1. So it's correct. So this matrix that I have, let's start putting the answer here. The answer, now remember, you have to keep these basis vectors in this order. And the coefficient matrix is going to be negative 1, 1. So negative 1, 1. Very interesting. Now let's do this one. So let's erase this. I want, let me erase all of this just so we don't have to see it. Oops. Okay, that was a little too much. Okay, so what I want to do is I want to write the matrix negative 1, 1 as a linear combination of 3, 2, and I believe the other one was 4, 3. So what is the C1 and C2 that make negative 1, 1? It's the same thing that we did before. The only difference, in fact, you can use all the same row operations here. The only difference is this column. So I'm going to subtract row 2 from row 1, and I get, we said 1, 1. This is going to be negative 2, 2, 3, 1. And then what I did was I added a negative 2 times row 1 to row 2. And I'll get, so this will be negative 2, 4. So 5, 0, 1. And then my last step is to subtract row 2 from row 1, and I'll get 1, 0, negative 7, 0, 1, 5. So you can see that C1 is negative 7 and C2 is 5. Let's plug those in. I always like to double check because sometimes when I put my matrices in reduced row echelon form, especially when I'm dealing with negatives, I'll make a mistake. Okay. Negative 7 times 3 is 21, negative 21. And this will be plus 20, so I get a negative 1. Good. And then for the bottom, I get a negative 14 plus a 15, which would give me 1. Great. So that tells me that what goes here is negative 7, 5. I'm almost done. I just want to write this matrix. I want to make it look a little bit nicer. So let's erase all of this. Okay. So now I'm going to say that I from B1 to B2 is equal to negative 1, 1, negative 7, 5. Okay. Now, we found the change of basis from B1 to B2. It's equal to this. What's the next question? What's the change of basis matrix from B2 to B1? So what is it asking me to find? I want this matrix I that goes from Now which way is it? From B2 to B1. Well, it goes backwards like this. B2 to B1. Let's look at the other one again. We went from B1 to B2, so these have to change. We're going from B2 to B1. There's two ways to do this. Let's talk about both of the ways. Now this matrix is equal to, we're taking vectors in V2. Let's review what the vectors were. I believe they were 3, I know one of them was 3, 4. Maybe I should just copy them. I think they're somewhere around here. Here they are. 3, 2, 4, 3. Let me copy these because I'm going to forget. Let's move them down here. So B2 was 3, 2, and 4, 3. And I want to write them in terms of B1. So two ways to do this. First way is exactly what we did the last time, which is we take the vector 3, 2, and we try to figure out a C1 and a C2 where we put 1, 1 and negative 1, 1, the vectors from B1 in that order. So this time, what we're going to do is we're going to solve for C1 and C2 by using this augmented matrix. Put this in reduced row echelon form. That shouldn't be hard. So let's see. I'm going to subtract row 1 from row 2. So I'll get 0. This will be 2. So negative 1. Then divide by 2. In the second row. And then the last step is to add row 2 to row 1. 1, 0, 0, 1. This will be, so this is 6 over 2, so 5 over 2, negative 1/2. Let's check that. So we said 5 over 2, negative 1/2. 5 halves plus 1/2 is 6 halves, that gives me 3. Then 5 halves minus 1/2 is 4 over 2, which is 2. So that's true. Now let's write the vector, maybe we should, I'm going to erase this now and put what the answer is, which is 5 over 2, negative 1/2. Now let's write this vector, C1, C2 here, and a 4, 3 here. Let's write this vector in terms of these. So the only thing that's going to change is we're going to put a 4, 3 here. We're going to do the same operations. So let's just erase this column. Okay, so what did we do? We subtracted row 1 from row 2. So this is negative 4, so negative 1. And then we halved this row. So this is a 4, and now this is a negative 1/2. And then we added row 2 to row 1. So this is 8 over 2. So this should be 7 over 2 and negative 1/2. Okay, so let's erase this and put those answers in. 7 over 2, negative 1/2. This should be 7 over 2, negative 1/2. Let's see, 7 halves plus 1/2, 8 halves, 4. 7 halves minus half, 6 halves, which is 3. That's correct. Okay, so now we have this matrix. So I, B1, B2 is equal to 5 over 2, negative 1/2, 7 over 2, negative 1/2. Okay, and we solved this, the change of basis from B2 to B1. Now, I told you there was a second option, and there is. Everything we did was right, and it's actually good that we did that because we really understand how to find this matrix. But remember what I said. I said that the inverse of this matrix is equal to this matrix. So recall the inverse of this is equal to I B1 comma B2. Now, since that's true, what I could have done after I found this matrix right here, which we're going to copy, if I just find its inverse, that should give me this matrix here. So this matrix, I'm sorry, it scrolled me down. Hold on just a second. I hate when it does that, but that's not a big deal. Here we are. Yeah. So this matrix I, B2, B1, that's equal to this. So then I, B1 comma B2 is its inverse. And how do we find this inverse? Well, we just put -1, -7, 1, 5, the 2 by 2 identity matrix, and then we try to get the identity matrix on this side. So let's do that. I'm going to add row 1 to row 2. So I get 0, -2, 1, 0, 1, 1. Divide this row by a negative. So let me write what I'm doing here. So I row 1 plus row 2, and then I'm going to divide this one by -2. So I get -1, -7, 1, 0, 0, 1, -1/2, -1/2. And then I just need to multiply this row by 7 and add it to row 1. If I do that, I'll get -1, 0, 0, 1. So I'm multiplying this by 7, so I have 7/2, -7/2. And this is a 2 over 2, so this will give me -5/2, -7 over 2, 1/2, -1/2. And then the final step is to multiply this row by a positive. So multiply it by a negative to make it positive. So positive, positive. So I got 5/2, 7/2, -1/2, -1/2. Let's compare that to what we had before. We said it was 5/2, 7/2, -1/2, -1/2. Exactly the same thing, just what we wanted. So that's two ways to do it. You have to figure out one side. So you have to do either this matrix or this matrix. But whichever one you find out, you could figure out the other one just by taking the inverse. Or you could use the process we used a little while ago.